So I've put together a little review of intermolecular forces for you guys. So pretty much everything in this video should sound familiar to you from Chem 1, but since intermolecular forces are so important for the AP test, I really wanted to make sure that you have a good foundation in it before we start to move on into the more complicated aspects or more involved aspects anyways, next week. So intermolecular forces are attractive forces between multiple separate molecules. And that is the most important thing that I want to emphasize in this video, is that you are taking two separate molecules and they're just attracted to each other. They're not bonding to one another, they're not attaching to one another, they're just attracted. They're like weak magnets, being attracted to one another just gently. And all intermolecular forces at their core are just electrostatic interactions between opposite charges. So essentially you can sum up intermolecular forces as opposites attract. And the most important difference, or thing to note, really, is that they're not bonds. People often confuse intermolecular forces with covalent and ionic bonds, thinking that they're kind of the same, or in the same class, or the same strength. And that's not true at all. We're going to talk about the relative strengths of the intermolecular forces, but all of them are much, much weaker than ionic or covalent bonds, which are intramolecular forces within one molecule. So if intermolecular forces are like weak magnets holding things together, ionic bonds or covalent bonds are like superglue. You can pull apart some weak magnets relatively easily, but two things that are superglued together are going to take a lot more work to pull apart. They're much, much more strongly held together. So intermolecular forces are responsible for a lot of properties that we observe or measure in the lab at the macroscopic level, and that's why they're so important, because they explain a lot of the things that we see in the lab and in our daily lives. So today we're going to talk about the four basic types of intermolecular forces. There are van der Waals forces, which are also known as London dispersion forces, or induced dipole forces. I will typically stick with London dispersion or dispersion, and that is what the AP test uses as well. We'll then go on to dipole-dipole forces, hydrogen bonding, and ion-dipole forces. But let's start with dispersion. So dispersion forces are present in everything. Whether it's polar or nonpolar, does not matter. All substances are capable of partaking in dispersion forces. So if you are asked to list what intermolecular forces is this compound capable of, dispersion always needs to be on the list for every single substance, no exceptions. Usually dispersion is the weakest of the intermolecular forces, but that's not always true. As molecules get larger and larger, the dispersion forces get stronger and stronger. So for some fairly large molecules, the dispersion forces can actually be stronger and more important than other intermolecular forces. And London dispersion forces are probably one of the most difficult to understand conceptually, but essentially what they are is they're an interaction between a temporary dipole and an induced dipole. So if you think about a nonpolar substance, it has a fairly equal distribution of charges. So in these molecules, in chlorine and Cl2, we have electrons symmetrically distributed all the way around the molecule in a cloud. But these electrons are moving. So at any given moment in time, if we were able to stop the electrons and see where every single one of them was, chances are really good that there's going to be a few more kind of bunched up on one end versus the other. And that creates a little bit of separation of charge. So where there just happen to be a few extra electrons, there's a little bit of negative charge, and where there happen to be a few less electrons, there's a little bit of positive charge. So this is what we are referring to when we say a temporary dipole. The separation of charge on these molecules is really, really small. So by Coulomb's law, we know that the attraction is going to be pretty weak, because the bigger the charge, the stronger the attraction, like we saw for ionic bonding the other day. So these charges are really tiny, so the attraction should be pretty weak. And when this temporary dipole comes into contact with another nonpolar molecule, the negatively charged end is going to repel some of the electrons in the other molecule. So those electrons start to move away, and in their wake, they leave behind a little bit of positive charge, putting negative charge over at the opposite side on the right. So the induced dipole force, or dispersion force, is the interaction between the negative end of one temporary or induced dipole and the positive end of another temporary or induced dipole. So this is the dispersion force. It's pretty weak, it's very short-lived, because these electrons are moving all the time. So in the next instant, in the tiniest fraction of a second, those electrons are going to shift back to the other side, which gets rid of the charge separation and makes it a nonpolar substance again. So now there's no reason for the induced dipole to remain a dipole. Its electrons move back, and that dispersion force dissipates, or shifts in the other direction to be between two different molecules. So they tend to be weak for that reason. As you get larger and larger, there are more electrons in your molecule, so there are sort of more opportunities for temporary dipoles to form. So that's why they get stronger as the molecular size increases. Dipole-dipole forces are next on our list. In order for a compound to be able to have dipole-dipole forces, it has to be polar. So if you're asked to list all of the intermolecular forces in a substance, you first need to determine whether it's polar or nonpolar. If it's a polar substance, it will have dipole-dipole as well as dispersion forces. These are typically stronger than dispersion forces. Again, not always, there are exceptions. The reason for that is that the dipoles are permanent and the separation of charge is generally larger. So the charge on the poles of your dipole is usually bigger in a permanent dipole than it is in a temporary dipole. And larger charges mean stronger attractions. And these are simply an attraction between oppositely charged ends of polar molecules. So if we look at something simple like HCl, it's a dipole because it is a polar bond. Chlorine is more electronegative, so it has a slight negative charge, and hydrogen is less electronegative, so it has a slight positive charge. When this is around another molecule of HCl, the negative end of one molecule is going to be attracted to the positive end of another molecule. And this is the dipole-dipole interaction. So they're just attracted because of their opposite charges, and that holds them together in some fashion. But again, they're not attaching, they're not bonding, they're just attracted. Hydrogen bonding is really just a dipole-dipole interaction. It's an especially strong one, but otherwise it's no different. And the name is really misleading because it's still not a bond. It's still an intermolecular force. So it's, compared to a covalent bond, very weak. Compared to other intermolecular forces, quite strong most of the time. So in order for something to be able to hydrogen bond, it has to be polar because it has to be able to do dipole-dipole interactions because hydrogen bonding is a dipole-dipole interaction. But it also needs some other special structural features. So in order for a sample of a pure substance to be able to hydrogen bond, in other words, for a molecule to be able to hydrogen bond with another molecule of itself, it has to be capable of being both a hydrogen bond donor and a hydrogen bonding acceptor. In order for something to be a donor, it has to contain a highly polar bond involving a hydrogen atom. So it has to have a nitrogen directly bonded to a hydrogen, or an oxygen bonded to a hydrogen, or a fluorine bonded to a hydrogen. You don't just need those two atoms in the same molecule, they have to be directly connected. So you can't have a nitrogen over here and a hydrogen over here somewhere, they have to be directly covalently bonded to one another in order to be a hydrogen bonding donor. To be an acceptor, you just need an electronegative element with a lone pair. So a nitrogen, an oxygen, or a fluorine with a lone pair of electrons on it. So if both of those conditions are met, then something can hydrogen bond with another molecule of itself. If only one of those conditions is met, then that molecule could hydrogen bond with a different compound, but not with itself. So hydrogen bonding is typically discussed in the context of water. Hydrogen bonding is responsible for a lot of the interesting properties of water. and water is a polar molecule, so it meets that criteria. It has an oxygen atom with 2 lone pairs on it, so it meets the hydrogen bonding acceptor criteria. And it has an oxygen atom directly connected to hydrogen atoms, so it also meets the hydrogen bonding donor criteria. So this diagram shows, with the blue arrows, where you would expect to see hydrogen bonding interactions. So you can see that the hydrogen atom from one water molecule is interacting with the oxygen of another water molecule. Because those have opposite polarities, the hydrogens have a slight positive charge, the oxygens have a slight negative charge. And again, it's just an interaction. They're not forming a bond. They're not reacting with one another. They're just attracted. And this tends to be a fairly strong attraction. The last force on our list is a little bit different because it only occurs between 2 different compounds. Everything else we've talked about can occur in a pure substance or between 2 different compounds, depending upon the context. But ion-dipole forces have to be 2 different things, because one of them has to be an ion and one of them has to be a dipole. So these tend to be quite strong electrostatic interactions because our charge is getting even bigger. A dipole has fractional charges on both ends. It might have a plus 0.1 on one end of the molecule and a plus 0.2, a negative 0.1 or 0.2 on the other side of the molecule. So they're small in general, but an ion has a full +1 or a full -1 or even a full plus or minus 2. So the charges are much bigger on an ion than they are on a polar molecule, which means, thanks to Coulomb's law, that the attraction will be stronger as well. So these are important, and we'll come back to them again when we're talking about dissolving things in water, creating solutions. So essentially what happens when you're dissolving an ionic compound in a polar solvent is that the polar molecules, polar water molecules most of the time, essentially surround the ions. And this process is known as hydration. They kind of create a little cage around the ions where the positive end of the water molecule is attracted towards the anion in whatever your ionic compound is, and the negative end of the water molecules is attracted towards the cation. So that's shown in this diagram. On the left, we have a chloride ion surrounded by water molecules, and on all of those waters, the hydrogens are pointing in towards the anion, because the hydrogens have the partial plus charge in the polar molecule. They're the positive pole of that dipole, so they want to be attracted towards the negatively charged ion. On the right, we have the sodium ion, which has a positive charge, so the negatively polarized oxygens in the water are pointed in towards the cation. So in summary, we have 4 major types of intermolecular forces. Generally, in order of strength, the weakest are London dispersion forces, which are present in everything. However, they can get strong for larger things, but for smaller molecules, they tend to be the weakest. Next up is dipole-dipole forces. They're present in all polar substances, but only in polar substances. Then hydrogen bonding is present in polar substances that have certain other molecular structural features. And ion-dipole forces tend to be the strongest between one ion and some polar compound. So you should be able to look at a compound when given a molecular formula and figure out which of these intermolecular forces do you expect it to be able to participate in, and which of these, or kind of rank molecules, relatively speaking, by the strength of their intermolecular forces that you would expect. So thinking about polarity and hydrogen bonding capability and size to see if maybe the dispersion forces are strong enough to kind of overpower something else, or at least that a large nonpolar molecule will have stronger intermolecular forces than a weak than a small nonpolar molecule. So at this point, that's about what you should be able to do. You should be able to finish that worksheet, and I will be collecting the worksheet on intermolecular forces the next time I see you. So have a great weekend.